Thanks for joining us today at Synthesis Workshop. I'm your host, Alicia, and for today's Research Spotlight episode, we're joined by Connor Delaney. Connor received his Bachelor's of Science in Chemistry from Northeastern University, followed by his PhD from the University of Illinois at Urbana-Champaign in the group of Scott, Denmark. He then moved to the Hartwig group at the University of California, Berkeley, where he was a Ruth L. Kirstein postdoctoral fellow. Connor is currently an assistant professor at the University of Texas, Dallas. And with that, I'll hand it over to Connor. Welcome, and thanks again for joining us.
Thank you very much for that kind introduction and for hosting me on the channel. Today I am excited to share with you all the story of our discovery of an unusual mechanism for the Ullmann cross-coupling reaction. And one cannot talk about carbon heteroatom cross-coupling without mentioning the Buchwald-Hartwig reaction, which uses a palladium catalyst to join an aryl halide and heteroatom nucleophile. The reaction was first developed in the 1990s and quickly gained popularity, becoming one of the most frequently applied reactions in pharmaceutical chemistry. However, nearly 100 years earlier, Olman and Goldberg had developed a method to forge the same kind of molecules using a copper catalyst. Now, the reason that the Buchwald-Hartwig reaction was revolutionary is that the Ullmann-Goldberg reaction, as it was originally described, was carried out at temperatures exceeding 200 degrees C. But the utility of the Buchwald-Hartwig reaction led to renewed interest in copper catalysis for the formation of carbon heteroatom bonds, both because of the lower cost of copper relative to palladium and because of the orthogonal chemoselectivity observed between methods catalyzed by copper or palladium complexes. The major turning point in the development of the Ullmann-Goldberg reaction was the identification of ligands that form catalysts that are active at much more reasonable temperatures. The method has now been developed to the point where it is applied in large-scale process chemistry, as highlighted by this multi-gram scale cross-coupling that was published in OPRD. These ligands generally fall into one of two categories: neutral bidentate ligands, termed LL-type ligands, and monoanionic bidentate ligands, termed LX-type ligands. And with powerful new methods for copper-catalyzed cross-coupling came a renewed interest in the mechanism of the reaction. What was discovered is that based on the identity of the coupling partners and the ligand used, the resting state speciation of the catalyst can vary wildly, but the type of turnover-limiting step does not. These methods generally proceed by turnover-limiting oxidative addition of a copper-1 complex into the carbon heteroatom bond. This proposal was initially controversial, as it was hypothesized that the copper-3 complexes proposed would be too high in energy to be implicated in the catalytic reaction. Alternative mechanistic hypotheses for the CX cleavage step included a copper-promoted nucleophilic aromatic substitution reaction, sigma bond metathesis reactions, and oxidative addition by a single electron pathway. However, careful studies by several research groups have ruled out these alternative mechanisms in a variety of different systems. In each case, the data support the involvement of copper-3 intermediates and a concerted oxidative addition step. So let's talk in a little more detail about the mechanisms of these reactions. When neutral ligands, such as those shown at the top of the slide, are used to form the active catalyst, the resting state species is a copper salt that can comproportionate to make the neutral heteroleptic copper complex shown. That complex reacts with aryl halide in a concerted oxidative addition reaction to generate a high-energy copper-3 intermediate that rapidly undergoes reductive elimination to form the new carbon heteroatom bond and give a copper-1 complex. That complex can exchange a halogen ligand for the nucleophile to complete the catalytic cycle. When anionic ligands are used to make the active catalyst, some features of the mechanism change, but the core steps remain. In this case, the off-cycle resting state is the homoleptic cuprate ligated by two equivalents of the nucleophile. Displacement of one equivalent of the nucleophile by the ancillary LX-type ligand forms a heteroleptic cuprate that once again reacts with aryl halide in a concerted oxidative addition reaction. Density functional theory studies show that the dissociation of a halide ligand precedes reductive elimination, and the copper-1 species generated once again re-enters the catalytic cycle. Beginning in the late 2010s, a new class of ligands has emerged that can potentially bind as a dianionic ligand. These ligands form catalysts that set records for turnover number with aryl bromide partners and enable reactivity with aryl chloride partners that rarely react with copper catalysts derived from LL or LX type ligands. The first of these was described by Dawei Ma, and a series of publications that highlight the utility of oxalimide ligands for copper-catalyzed cross-coupling. The Hartwig group has also contributed the finding that oxalohydrazide ligands form catalysts that reach exceptional turnover numbers over 8,000 for the cross-coupling between aryl halides and phenoxide. And more recently, researchers including Buchwald, Cook, and Shikar have identified other ligand scaffolds that also give rise to exceptional catalyst performance and could bind in a dianionic mode. And so, when I joined the Hartwig group as a postdoc, I set out to understand the mechanism of these transformations. We began by investigating whether the critical oxidative addition step involved the reaction between an aryl halide and a copper-1 complex of a monobasic LX-type oxalimide ligand, as had previously been proposed, or if it was an oxidative addition reaction between a copper complex bound by an XX-type dianionic oxalimide ligand. To do so, we proposed to synthesize the relevant copper complexes and then investigate their reactivity with aryl halide electrophiles. The reaction between mesotale copper and the monopotassium salt of the oxalimide ligand shown gave a complex that we named the monoligated cuprate, which has a 1-to-1 ratio of copper-1 and the dianionic oxalimide ligand. X-ray crystallography provided a connectivity map that established the structure as a dimeric species with 2 copper atoms and 2 dianionic oxalimide ligands. With that complex in hand, we could use it to prepare the heteroleptic cuprate, that in one hypothesis could react with the aryl halide in the turnover-limiting step. That complex was identified by electrospray ionization mass spectrometry. Unfortunately, we were not able to isolate the complex because it is in equilibrium in solution with the 2 homoleptic cuprates shown. Nonetheless, we investigated the reaction between the heteroleptic cuprate and 1-bromo-4-fluorobenzene, monitoring the consumption of starting material and the formation of product by 19F NMR spectroscopy. Upon addition of the aryl halide, the copper-1 complex was immediately consumed without the formation of biaryl ether product. After extended heating, the biaryl ether was ultimately formed in 20% yield, along with 30% of fluorobenzene and 33% recovered starting material. The selectivity of this reaction was very far from the near quantitative yield that was observed for the catalytic reaction. Altogether, these data led us to rule out the intermediacy of the heteroleptic cuprate. Next, we considered the intermediacy of a copper complex of a dianionic oxalimide ligand, the monoligated cuprate. Progressive addition of phenoxide to a solution of the monoligated cuprate led to a monotonic change in the chemical shift of several resonances in the proton NMR spectrum. Based on the data shown, we conclude that the phenoxide reversibly binds to the monoligated cuprate to make a dianionic copper complex. To test the intermediacy of such a complex, the monoligated cuprate was again combined with a phenoxide nucleophile and then with aryl halide. As in the previous experiment, the copper complex was immediately consumed without the formation of product, and 25% of the aryl halide was consumed as well. Heating the reaction for 20 minutes at 100 degrees C led to a 75% yield of the biaryl ether product, along with a 25% yield of the reduced aryl halide, the fluorobenzene. Once again, these data were inconsistent with the intermediacy of a copper complex bearing phenoxide and the dianionic form of the oxalimide ligand. Factors including the color of the solution, the disappearance of the ligand resonances from the proton NMR spectra, and drastically decreased T1 relaxation times of the observable protons in solution, along with the presence of the fluorobenzene reduction product, all suggest that the copper-1 oxalamide complexes are very rapidly oxidized to NMR-silent copper-2 complexes when they are combined with aryl halide. However, after all the copper-1 has been consumed, heating the reaction results in the formation of product. So both hypotheses have been ruled out, and the data support the formation of a copper-2 species in the reactions. So we were left to consider the hypothesis, could a copper-2 complex actually be promoting this reaction? To investigate, we started a collaboration with the EPR experts in the Brit lab at UC Davis. Doctors Lizzie Tao and Guodong Rao were enormously helpful in characterizing the copper-2 species in solution. The EPR spectra show that in each experiment, a single copper-2 species was formed. Furthermore, we were able to resolve the hyperfine splitting pattern in the G parallel signal, which clearly shows that the unpaired electron on copper couples to 4 nitrogen nuclei. The most likely species that fits the description is the copper-2 species ligated by 2 oxalamide ligands. The reaction of the oxalamide ligand with copper-2 bromide in the presence of base led to the formation of an emerald green copper-2 complex that is bound by 2 dianionic oxalamide ligands. Here I'd like to give a shout out to Hartwig group member Angew, who collected the structure and solved it, and provided all X-ray crystallography support for this work. EPR data shows that the complex shown is also formed in the catalytic reaction and each of the stoichiometric reactions that I had previously discussed. Having identified the copper-2 species that was formed in the reactions, we next had to determine whether that copper-2 complex was an active catalyst or was a pre-catalyst that must be first activated by a reaction with one of the coupling partners. Prior studies have shown that in most cases, when copper-2 salts are added to a Ullmann or Goldberg reaction, they are reduced in situ to form an active copper-1 catalyst. To test this hypothesis, we carried out an experiment in which each coupling partner was reacted with an equimolar amount of copper catalyst, as shown in the scheme. If the added copper complex is the active catalyst, we should observe a near quantitative yield of the biaryl ether product, with reaction kinetics that reflect the order in the limiting reagent. However, if the copper complex is a pre-catalyst, one of 2 scenarios will be operative. If the rate of catalyst activation is faster than the rate of cross-coupling, the limiting coupling partner will be consumed in the activation reaction, and little will be left for the coupling reaction, leading to a low yield of biaryl ether. If instead the rate of activation is much slower than the rate of catalysis, we could observe partial activation of the catalyst and a high yield of biaryl ether. In that scenario, a significant induction period would be observed. When we executed the experiment, we found that the copper-2 complex was indeed an active catalyst for the reaction. The reaction of limiting aryl halide with excess potassium phenoxide in the presence of 1 equivalent of copper catalyst led to a 99% yield of the biaryl ether product, with clean first-order reaction kinetics, and this result shows that the aryl halide does not convert the dipotassium bisligated copper species into a new active catalyst. More significantly, when the potentially reducing phenoxide partner was the limiting reagent and reacted with excess aryl halide, we observed clean zero-order reaction kinetics through 70% of the reaction course and ultimately a yield of 97% of the biaryl ether with respect to the initially added phenoxide. These data show that phenoxide is not reducing the copper-2 complex to an active copper-1 catalyst, and they starkly contrast with the prior experiments done stoichiometrically with copper-1 complexes. With the catalyst resting state established, we next considered the kinetics of the reaction to determine the stoichiometry of the transition state relative to the resting state. Focusing on the most important reaction orders, we observed an inverse rate dependence on the concentration of ligand, suggesting that a ligand reversibly dissociates prior to the turnover-limiting step. A roughly first-order rate dependence on the concentration of aryl halide shows that the aryl halide is associating prior to the turnover-limiting step, and a zero-order rate dependence on the concentration of phenoxide shows that phenoxide is either present in both the resting state and turnover-limiting step, or is absent in both. To distinguish those two scenarios, we carried out a Hammett experiment varying the electronic character of the phenoxide nucleophile. There was no dependence of the reaction rate on the electronic character of the nucleophile, suggesting that the phenoxide is not bound in the turnover-limiting transition state and therefore not bound in the resting state as well. Furthermore, a stark dependence of product ratio on phenoxide electronic character was observed when the Hammett experiment was instead run in a competition mode, which strongly supports our conclusion that phenoxide enters after the turnover-limiting transition state. With an understanding of the resting state and the path between the resting state and the turnover-limiting step, we were left with a familiar question. What is the nature of the turnover-limiting oxidative addition reaction? Now, oxidative addition in a concerted fashion to a copper-2 complex would form an intermediate with an abnormally high valence. So we return to the alternative mechanisms that have been proposed because they avoid a high oxidation state on copper. First, we will consider a mechanism involving turnover-limiting sigma bond metathesis. In that mechanism, phenoxide must be present in the turnover-limiting transition state, and that is contradicted by the data that has been presented so far. This allows us to rule out the hypothesis. Next, we consider the mechanism involving a turnover-limiting copper-activated nucleophilic aromatic substitution reaction. This mechanism is only consistent with the zero-order rate dependence on phenoxide if the turnover-limiting step is coordination of the aryl halide to copper. In that scenario, we predict no 13C kinetic isotope effect on the carbon that is bounded to bromine because the carbon-bromine bond is not cleaved in that step. In both inter- and intramolecular experiments to measure kinetic isotope effect, carried out by the methods of Singleton and Vedicat, we observe a primary 13C kinetic isotope effect, demonstrating that the carbon-bromine bond is broken in the product committing step. Thus, we can rule out a nucleophilic aromatic substitution reaction as the turnover-limiting step. Next, oxidative addition by a radical mechanism could avoid the formation of high-valent copper intermediates. That mechanism involves the intermediacy of aryl radicals. To test for aryl radicals, we employed a well-known radical trap, an aryl halide with a pendant alkene. When an aryl radical is formed, a rapid 5-exotrig cyclization takes place to give rise to cyclized products. When we reacted that aryl halide with potassium phenoxide, no cyclized products were observed, and that observation is in good agreement with the results of analogous studies previously carried out by the Ma group. So we have once again ruled out all our competing hypotheses. All the data support a concerted 2-electron oxidative addition reaction as the turnover-limiting step. Anticipating that the product of such an oxidative addition reaction would be prohibitively difficult to study experimentally, we turn to density functional theory to explore what the electronic structure of such a complex might be. To avoid challenges associated with the study of charged molecules by DFT, we limited our study to the oxidative addition step, beginning with a neutral copper-2 complex bound by a single dianionic oxalimide ligand. Association of aryl halide to that complex was found to be endergonic by 12 kilocalories per mole, and the overall barrier to oxidative addition was calculated to be 23 kcals per mole. More significantly, NBO calculations show significant radical character on one arm of the ligand in the high-valent copper intermediate that arises following oxidative addition. This shows that copper avoids a prohibitively high formal valence by oxidation of a ligand in a process known as ligand non-innocence. And here I'd like to give a huge shout out to Eric Wang, a visiting undergraduate student who joined the Hartwig group for only several months, but was responsible for the majority of the DFT work done in the paper. Altogether, the data support a mechanism in which the resting state of the reaction is a copper-2 complex bound by two dianionic oxalamide ligands. After reversible dissociation of one ligand from that complex, a turnover-limiting concerted oxidative addition reaction happens between an aryl halide and the copper-2 complex. Phenoxide then enters the cycle after the turnover-limiting step, and reductive elimination regenerates the copper-2 catalyst. In practical terms, what we have learned is that the active copper-2 catalyst in these reactions is incredibly robust, in contrast with the frequently employed catalysts that are based on copper-1. As one example of this, the coupling reactions set up with copper-2 as a catalyst were entirely unaffected by the presence of air, because the copper-2 complex is not susceptible to aerobic oxidation. Additionally, we found that by adding the copper-2 resting state directly as a catalyst, instead of relying on its formation in situ, we could achieve a remarkable turnover number with an aryl chloride electrophile of over 1,000 turnovers. Although the rate of this reaction is not quite sufficient to be preparatively useful, it is remarkable that the catalyst achieves such a high turnover number, much higher than has been previously observed for aryl chloride electrophiles, but also that it continues to be active after multiple days of heating at 130 degrees C, highlighting the robustness of the catalyst. And these studies on the preparative uses of the copper-2 catalyst were carried out by Eva Lin, a former Hartwig Group undergraduate, now graduate student in the Macmillan Lab at Princeton. In conclusion, we have determined that a copper-2 complex catalyzes the Ullmann cross-coupling reaction. The resting state of the system is copper-2 complex ligated by two dianionic oxalamide ligands, and one of those ligands dissociates prior to a turnover-limiting concerted oxidative addition. The oxidative addition to the copper-2 is enabled by ligand non-innocence, and directly adding the resting state complex enables cross-coupling reaction of an aryl chloride with over 1,000 turnovers. And so, first and foremost, I would like to thank Professor John Hartwig for his support, mentorship, and guidance over the course of this project. Our collaborators at Roche, Dr. Serena Fantasia and Dr. Kurt Puntener, who provided support and guidance throughout the project. Professor David Britt, Lizzie Tao, and Guodong Rao for their support with EPR spectroscopy, Eva Lin, both for her efforts in the development of the catalytic reactions, as well as general support on many of the things that I've presented today, Eric Wang for his contributions to the DFT section, and finally Anna Jed, who contributed to various Hammett studies. Funding for this project came in part from Roche and in part from an NIH F32 fellowship. Last but not least, I'd like to thank you all very much for listening.
Thank you to Connor for this spotlight on the mechanistic studies of a copper-2 catalyzed Olman cross-coupling. If you would like to learn more, please visit Connor's recent publication in Science. If you've enjoyed this episode and would like to support our podcast, please consider subscribing to us here on YouTube or following us on Twitter. Thanks again, and we hope to see you next time.